So Mike and I are doing the warm-up talk for today. Anyone who didn't hear, my name's Alyssa. I'm also one of the organizers for this conference. I am slightly underprepared, and I feel highly underqualified to be giving this warm-up talk, but apparently I'm doing it anyway. It is a very general and also a very abbreviated introduction into astronomy and planetary science, just because we don't have enough time to do everything. So I'm trying to touch on some of the topics that will be discussed for this morning's talks, so anything astronomy and planetary science based. So I guess we'll just get started. So introduction to planetary habitability. Habitability is one of the biggest things, in my opinion, in astrobiology right now, because we have Kepler Space Telescope and lots of other things that are helping us to find these exoplanets. So a big thing is, how would we be able to tell whether or not these exoplanets that we're discovering, if they're habitable or not? There are a variety of characteristics that affect planetary habitability, including composition of the exoplanet, any atmosphere, stellar radiation, tidal evolution. I'm not going to get to all of those, but just so you know that they do exist and they are a factor in planetary habitability. So the first thing in exoplanets that I wanted to introduce is how we detect them. How do we actually find these exoplanets? And now that I'm involved in my talk, I'd like to point out that you guys are welcome to get up and wander around during the time if you want to go get more coffee or more food. It's supposed to be informal, so you don't have to stay put. Sorry, moving on. Okay, two primary ways to detect exoplanets. First way is called the radial velocity method, or alternatively, Doppler wobble. How this works. I need my hands. That's okay. When you have if this hand is the sun and this is a planet or something, when two objects are orbiting around each other, the smaller body stays in orbit due to the gravitational tug of the larger body. But in that same vein, the smaller body will also exert a gravitational pull on the larger body. It happens, so the two things orbit their common center of mass. So it's an imperfect image because it's exaggerating the gravitational pull. All right, people keep crossing in front, that's all right. So in this case, we have one sun that's in the center and then an exoplanet orbiting the outside. The point to take away from this image is that as the exoplanet orbits around the star, there's a slight wobble, a slight shift in the radial velocity of the sun. And you can measure the slight velocity wobble based on the redshifting of the color that we receive from the star. So when a star is moving away from us, the color will be slightly red-shifted, and when a star is moving towards us, it will be slightly blue-shifted. So in this way, we can look at a star and we watch over time, and we see the light become red-shifted and then blue-shifted and then red-shifted and then blue-shifted, and you can infer the presence of an exoplanet because there has to be some body that's orbiting that sun that is causing the shifting of the light. So this is one way to detect exoplanets. Second way is using transits. Sorry, I keep combining hands. Transits are not quite as complicated as Doppler shift. The whole point, the big circle, hey, I have a pointer. The big circle in the background, this is a star, right? When you are just looking at a star, you measure some amount of light coming from the star, which is what we see as this solid line right here. But periodically, you're going to have a planet, or well, we don't know it's a planet. There's something that passes in front of the star and causes, it blocks some of the light that we receive from the star. So this is just a dip in the light levels that we're observing because there's something obscuring the view of the star. So we can't see this. This is the part that we can't see. Very rough analogy, if that doesn't make a lot of sense. If you imagine a car at night, if you're standing right up close next to the car, you can see both the car headlight and any insects that are flying around the car headlight. But if you turn around and walk away from the car and then look back, you can still see the car headlight, the sun, but you can no longer make out the individual insects. It's just because you're too far away and you can't see the size of the insects. So it's the same thing with exoplanets and suns. We can't actually see this, but we can detect the change in the light levels when a planet transits in front of a star. And just in terms of vocabulary, you'll hear transit and occultation. A transit is what happens when a planet passes in front of a star, and the occultation is the same thing, but when the planet passes behind the star. So it means the same thing. It means you're blocking out light. It's just whether it's in front of or behind the star. I had someone ask me yesterday about uncertainties. So I just wanted to throw up a set of example data so you know what real data looks like. So all of these dots with their error bars on them, this is an example set of data. Here, you know, our average amount of light that we're receiving from a star is here, and then periodically you'll have this dip in the light level. And just to see this dip once is not enough, but if you observe this over time and you see that dip repeated numerous times, again, the implication is that there has to be a planet there. There has to be something orbiting the star that is causing this dip in light levels. Which is Kepler. Everyone, I hope, has heard of Kepler. Anyone who does planetary science is really, really excited about Kepler Space Telescope. This is a space telescope and not a ground telescope. That means that it's in space and not on the ground. It's the only distinction. There are a variety of benefits for that. An example being that if you're in space rather than on the ground, you don't have to deal with light, like light pollution coming in and affecting the mirrors and stuff. So this is just an artistic rendering of Kepler. What do we have? Yeah, Kepler, the sole point of the Kepler Space Telescope is to find exoplanets. That's kind of its whole job, which is why it's exciting. At any one time, it simultaneously looks at over 150,000 stars. So it's not just looking at one little spot of light and finding planets. It can do it for a wide variety of stars all at the same time. It has that photometer, the thing that measures the light level, and you see the dip in it. That's the photometer. Kepler was launched in 2009. Anyone who's heard the news, we sadly just lost a second wheel on Kepler, which means we can't really steer it anymore. So we can't actually aim it at one point in the sky. We're not sure what's going to happen with Kepler, but it's very sad. The last numbers I was aware of, that Kepler has discovered almost 3,000 candidate exoplanets. And as of right now, there's only 114 that have been confirmed as exoplanets, but that's still a pretty impressive number. You know, that means we do know that there are real exoplanets orbiting distant stars. And if you extrapolate the data from the part of the sky that we've looked at, scientists, other scientists estimate that at about 17 billion Earth-sized exoplanets in the Milky Way alone. So impressive. This is just an example set of data. So these are the 114 confirmed exoplanets that we have from Kepler. We're looking at here, this is planet mass on the y-axis and semi-major axis on the x-axis. Semi-major axis is just orbital radius. That's how far a planet orbits from its star. Also note this is on log scale. So we are right here. We're at 1,1. We're at 1 Earth mass and 1 astronomical unit from the sun. You can see, so there are rough groupings, and I'm not going to get into the groupings. What I am particularly interested in, and I'm going to talk about in just a second, are the SuperEarths, which are in this range right here. They're kind of this oval collection of planets. And just to illustrate a point, these are the 150 confirmed exoplanets. These are the almost 3,000 candidate exoplanets. So they have not been confirmed yet, but you can see they do follow the same trend. So hopefully, when we get enough data, we can confirm more of those candidate planets as confirmed exoplanets. So that was an introduction to detection and how we do that stuff. I want to take just a minute and go into some theory behind SuperEarths, because that's kind of my thing, SuperEarths. What is a SuperEarth? A SuperEarth is a class of exoplanet with a mass between 1 and 10 Earth masses. So we're at 1 astronomical unit. The distance from the Earth to the sun is 1 AU. SuperEarths are less than 0.2 AU, so they orbit very, very closely to their parent stars. They do have some eccentricity, and I'll talk about that in just a second. That just means how oval your orbit is. If you're not traveling in a perfect circle around your star, you're in an eccentric orbit. SuperEarths are primarily terrestrial, which is exciting when we come back to astrobiology, because the assumption right now is that to find a habitable planet, it would have to be terrestrial like the Earth. Sorry, it's too early to talk this much. So primarily, they're terrestrial. Secondarily, they are ocean worlds. They have no solar system counterpart. Like I said, they're up to 10 times the size of the Earth, and they orbit even closer to our sun than like where Mercury orbits, roughly. There's a variety of characteristics about these. Again, I'm not going to have time to go into all of them, but just so you know that they exist. I'm going to talk briefly about their composition, the interior of the SuperEarths, any tectonic activity that goes on, because that's a pretty key thing, and also how atmosphere and how all those things affect habitability. How are we on time? Are we okay? We're okay. So this, just in case I lost anyone with a little bit more terminology for anyone who doesn't do planets. In this case, the yellow blob in the middle, that's a sun, and the blue planet here is on a perfect circular orbit. And in that case, the eccentricity we say is 0. It's a perfect circle. In the case with the red planet, you kind of have this fried egg picture right here. The fried egg image with an oval orbit means that you have eccentricity. The eccentricity is not 0. And again, semi-major axis is just the orbital radius, the distance between the planet and its star. So composition, I'm going to try to not make it too scientific. When you model the interior of SuperEarths, you have 3 different things. You have an ice mass fraction, a mantle mass fraction, and a core mass fraction. And you just model those 3 different homogeneous concentric shells. The outer layer is all water. It can be either liquid or frozen, but it's a water outer shell. You have a silicate mantle in the middle, and you have an inner core of either solid or liquid iron. So these are these 3 basic assumptions about bulk composition for SuperEarths. But given what I was talking about with detection, when you have radial velocity data, we can feel that Doppler wobble. The Doppler wobble tells you the mass of an exoplanet. And with the transit data, that gives you the radius. So if you have basic information about the mass and the radius of a planet, you can infer something about its bulk composition, which is what leads us to this theory for super-Earth interiors. This is the most scientific slide I'm going to show, but don't be too frightened. Again, it's just those 3 mass fractions. So we have ice, mantle, and core mass fractions. This is called a ternary diagram. Each of these different sides just measures a different fractional amount of the ice, the mantle, and the core. So the best example, because we were just saying, to be habitable, we're assuming that an exoplanet is going to have to be terrestrial. There has to be, something to stand on. Like we can't stand on a Jupiter, so that would be pointless. So in this case, water is measured here. It's this, anyway, hold on. So right here, this is when water is 100, and this side is when water is 0. So we call this side the terrestrial side. There's no significant water presence on a planet. And the whole point of a ternary diagram is because it's a grid representation of the relationship between the water, the mantle, and the core mass fractions. So we can actually throw some science and some theory and some other stuff in here and get a working equation for the relationship between these 3 mass fractions when you model super-Earths. So to be habitable, right now, we're looking at anything that falls on the terrestrial side of this ternary diagram. Very briefly, plate tectonics, for anyone who's unfamiliar. I know Jess is doing the geo talk tomorrow, so I'm not going to spend a lot of time on this. There are 2 main ways to transport heat, and we have to transport heat in an exoplanet. You have conduction and convection. Rock is a really sucky conductor, so we're not going to work with conduction. There are 2 main ways of having convective cycles in a planet. We have either stagnant tectonics, or I'm sorry, stagnant lid stuff, or actual plate tectonics like on Earth. So stagnant lid is when you have no plate tectonic activity. It's just an outer crust of a planet that has cooled off more than the interior, so the heat bursts its way through the crust like these little, like all the volcanoes that are on Io. That's an example of stagnant lid. As opposed to something like Earth, which does have plate tectonics, and in that case, this is this image here. So you have these convection cells that are carrying the heat. Material is created at the mid-ocean ridges here, and then the plates slide apart, and then they're recycled down in the subduction zones. So these are the 2 big arguments and theories for which super-Earths do. The arguments being that super-Earths, because they're so much more massive, their gravity has increased, which is going to cause an increase in pressure. And these people say that the pressure is going to be so great that it's going to actually cause fault locking, and the plates are not going to be able to deform at all. So you're going to have a stagnant lid system. The other side of the argument say that the increased mass of the super-Earths is going to cause an increase in stress. And when you have an increase in stress, the plates will be more easily deformed. So we haven't actually confirmed this one way or the other, but just so you know, there are arguments out there. Basic introduction to atmosphere. I do not work in atmospheres, so again, underqualified to give this talk. We have a couple people doing atmospheric things. The point I just wanted to make without being too scientific is that we can measure we can detect the atmospheres of some of these exoplanets. And if we find things in the atmosphere like carbon dioxide or water vapor, some other things, those are what we call biosignatures, and they indicate the presence of life on a planet. So for example, something like oxygen. Oxygen is unstable on its own. So when we have oxygen in the atmosphere on Earth, we know oxygen is only there because there's life on this planet. So kind of a rough assumption, but we'll go with it. If we found something like that in an exoplanet atmosphere, it would not necessarily guarantee the presence of life, but it would be like, hey, that's something to look at because there's some biosignature there. And how that happens is something like this. So this is again, so here you have, oh God. Here you have the transit in front and the occultation in back. And when the planet passes in front, you take an image of the star by itself, and you take an image of the star with the planet in front, and you do, I don't know what it's called. It's like a negative. You take the difference of the two images, and what you're left with, like if you subtract, I don't know how to explain this because I don't do it. If you take an image of just the star and then an image of the star and the planet, if you subtract them, you're left with the image of the planet or something like that. And you can magically, you can see this little blue shell. You see the atmosphere, and you can get a spectrum. And when you have a spectrum, you can infer based on where the peaks are, what the chemical makeup is of that atmosphere. So it's possible, was my point. You can do that. Habitability, short thing for habitability again. Earth is currently the only planet that we know to be inhabited. And because of that fact, it's kind of the only thing that we're left with when we talk about habitable zones and what it means to be a habitable planet, just because it's the only thing we know. So we define something called a habitable zone. A habitable zone is the distance from a star for which a planet can support liquid water on its surface. So you're going to have an inner edge and an outer edge of the habitable zone. If you're in this nice band going around your star, if you're on the inner edge of the habitable zone, if you're too close to the star, you're going to get a runaway greenhouse effect because everything's going to be evaporated, which is kind of what we see on Venus. If you're on the outer edge of the habitable zone, you're too far away from the star, and everything's going to get too cold, and you're going to have a runaway glaciation effect. Everything's going to freeze, which is not really what we see on Mars, but work with me here. Call this the Goldilocks zone, Goldilocks principle, too hot, too cold, right in the middle. I like this one just because this image, just because it kind of shows you what I mean with the whole habitable zone thing. So here we have our sun on the top, and these are our planets going across the top line here. You see Mercury. Mercury is very, very far within the habitable zone. Sorry, the blue band is our habitable zone. Mercury's not habitable at all. Here's Venus. It's kind of on the inner edge of the habitable zone. It has that runaway greenhouse effect. Here's the Earth, right in the middle of this blue habitable zone. We exist, happy us. And here's Mars, and again, it's not an exact science, this image, it's just kind of illustrative. So we have Mars that's close to the outer edge of the habitable zone. And we do have someone talking about M-dwarfs today. I believe Gliese 581 is an M-dwarf. Yes, good. Gliese 581 is an M-dwarf, excellent. And Gliese 581 has a whole bunch of planets, which is really exciting. G, the planet Gliese 581G, is right in the middle of its habitable zone. The sad part about Gliese 581G is that we think it doesn't actually exist. But ignoring Gliese 581G, let's look at Gliese 581D, which is still at least kind of sort of borderline in the habitable zone. So that just means that, look, we found an exoplanet, and it's kind of sort of almost in the habitable zone, so maybe there could be life there, type stuff. The other thing to note, all of this talk about habitable zone is based solely on the assumption of having liquid water present on the surface of the planet. There are lots of other characteristics that come into play when you really want to consider whether or not a planet is habitable. For example, tidal locking. This in no way takes into account tidal locking. So tidal locking is when two orbiting bodies show the same face to each other all the time. So easiest analog again would be like the Earth-Moon system. The moon is tidally locked to the Earth, which is why we always see the same face of the moon. The moon does not seem to rotate. I'm not explaining that very well. If you have two things like this that orbit like this around each other, they are tidally locked because you always see the same face. That's my point. Those were moons. Sorry. So yes, tidally locked. Moon is tidally locked to the Earth, which is just another factor. I don't have an image of that, sorry. Exomoons, I just wanted to touch on briefly. I think we have a couple talks about exomoons as well. Oh, and a note that I forgot to put earlier. The habitable zone does shrink when you consider smaller stars. This is on a log scale. So back here, the habitable zone is actually wider than it is up here. When you have a smaller star that is, there's less heat and less energy and stuff coming off of something like an M-dwarf. So the habitable zone both moves inward closer to the star and also becomes narrower. So it's a narrower band of habitable zoneness. Moons, I just wanted to mention real quick. Like an exoplanet, so an exoplanet is an extrasolar planet. An exomoon is an extrasolar moon. It's just a moon that orbits an extrasolar planet. If they exist, it would be really, really nice if we could find them to be roughly Earth size, because there is possibility to have a habitable exomoon besides just a habitable exoplanet. And the upside of looking at exomoons this time is this thing still on? Good. The upside of looking at exomoons this time is because they're going to be, hopefully, a lot more numerous than the exoplanets. If you consider planets that are the size of Jupiter and Saturn right now, they have a whole lot of moons. So we're hoping that if we can find these huge super-Earths that are really, really large, maybe they would have a similar increase in, what am I saying? If you have 100 exoplanets, and each one has 10 moons even, you've already increased the number of potentially habitable bodies. So we're looking at exomoons as well. This is just an image from Renee Heller as an example exomoon system. So here we have a hypothetical Earth-sized moon that is orbiting this orange exoplanet in the background, and there its star is its star in the background. So just an example system. I also wanted to mention Triton. This exomoon stuff, I'm not going to do a lot about the capturing, but just so you know, Triton is one of the coolest moons in our system. It is a moon of Neptune, and we think it might be captured because it actually travels, I don't know what the word is. Is it retrograde? Thank you. It travels backwards. Like all the other moons are going this way, Triton's swimming upstream. So Triton's cool, and it has an atmosphere, and it has some nitrogen sublimation stuff going on, so it's cool. Someone's talking about Triton. There it is. Good, so that's mostly the end for me. What was the point? The point was that there are a lot of factors that you have to consider when you're talking about planetary habitability, especially with this new science of exoplanets. Super-Earths are going to be the big thing in exoplanetary science with relation to habitability and astrobiology. Exomoons are really a new thing, so exoplanets started relatively recently. Moons are even really, really more recently. Good job. The largest moon in our system is Ganymede, which is still only 0.25% Earth size. Thanks to Kepler, we have a whole lot of planets that we're discovering, and we have all these great ways to detect exoplanets right now. So we have Doppler wobble, we have transit data, all this sort of stuff. And hopefully science will keep going, and we will eventually find a habitable exoplanet or exomoon. And if we have just a couple minutes, I can do questions. Otherwise, we will carry on to Mike, who is going to introduce the second half of today's talks. But I think I have like 3 minutes if anyone has a quick question before Mike takes over. And if not, we'll just do them all at the end. Yay!